Alright, so welcome to the video. In this video we are going to see the basics of how we can perform a CFD analysis using ANSYS Fluent. So our geometry will be a sphere of diameter 10 centimeters. So let's try to model that first in Fusion 360. I'm going to create a sphere and the diameter is 100 mm. So this is the geometry of our sphere. Now what I'm going to do is create a bounding box like a wind tunnel, which we will then use to create the fluid domain. So this is a simple geometry of the fluid domain. So if you go for the recommended Simscale aerodynamics tutorial, here the standard fluid domain dimensions will be given. So the upstream dimension should be 3 times the length of the object. So let this make it as 300 mm, and height should be 3 times the length of the object. So we will make it this one as 300 and this one also as 300. And length as 8 times the length of the object, so that is 800 mm. And I'm going to finish the sketch and extrude this to one of the side, and if you see, the width is also 3 times the length of the object, so it will be 300 mm. I'll make this as a new body, and what we need to do is we are creating a symmetric bounding box, so we will subtract using the combine feature. And now you can see there are 2 bodies, and this is the sphere. So we subtracted or removed the object from the fluid domain, and the symmetry boundary condition will be applied on this particular face. Let's save this file. And I want to export this geometry by converting it into a component. And then I will export this geometry into step format. So export is completed. This is our step file of the CFD sphere. And now we will open ANSYS. Alright, so now we are into the ANSYS. So to do the fluid flow CFD simulation, we will double click on the fluid flow fluent module, and we will give a right click on the geometry and import our STP file. And now we will generate the mesh. So here is our geometry. So we have the sphere and we have these faces. So first of all, before meshing, I will give name selection. I will call this as inlet. And I will call this particular face as outlet. And this wall as symmetry. Give a right click and go to create name selection, and I will give this name as walls. And finally we have this particular inner sphere face. I will simply call it as sphere. And inside the mesh, I will create some sizing. And element size, I will give it as, so our geometry length is 100 mm. So if you divide it into 20 mm, so it will be 0.02 meters. And then I will give inflation layers. And I will select the face of the sphere, and I will select this as the boundary. And I will inflation option, I will give it as first layer thickness. And in order to calculate a first layer height, we need to use the y plus. So y plus is the non-dimensional boundary layer height. So our free stream velocity will be around, we will keep it as 1 meters per second, and density of air is 1.2, and dynamic viscosity of air is 1.8 into 10 power minus 5, and we will input as boundary layer length. Boundary layer length is nothing but our length of the sphere, so that is 0.1 meters, and desired y plus value I will keep it as 30, and I will estimate it. So the Reynolds number is in laminar flow, so we'll try to increase the velocity. Let's say this is as 10 meters per second. So this is roughly touching the turbulent boundary layer, turbulent region of the Reynolds number, and estimated wall distance is 0.8 millimeters. So I will input the same thing in the software. So 8 into 10 power minus 4, that's what I have given. That is estimated wall distance. Maximum layers I will give it as 5 and growth rate of 1.2, and then I will click on generate the mesh. Let's see what kind of a mesh we are able to generate. Some error is coming, sweeping failed because there is an existing mesh or one or both on one or both of these faces. So I will resolve this issue. So I have changed the settings. So the mistake that we did was we didn't select the geometry properly. So select the whole body like this and click on apply, and this is the boundary. So you select the face of the sphere to apply the inflation layers, and here you are going to give the inflation boundary status using the first layer thickness, and here the first layer height is going to be 0.0008, and regarding the body sizing I have given it as 1 centimeter, that is 0.01 meters. And now you click on generate mesh. So it is going to generate the mesh for us. So here we go, this is our mesh. So let me rotate and show you how the mesh is generated. This is the overall mesh of the CFD domain, and we have inflation layers. So you can see that the first layer height is 0.08 millimeters. So now we are going to save the Workbench file. Click on update on the mesh. It is going to update the mesh for us. And I am going to save this project file, CFD of sphere. And now I am going to take you to the Fluent. And this is the Fluent interface. So this is our mesh. So I will go to general. So keep this as pressure based and velocity formulation as absolute, and keep this as steady state, and go to the models and change the model. Click on edit, and now we are going to select the K omega SST model. So that is the turbulence model, and leave all the remaining parameters as the default. And click on OK. And click on materials. We have air, create or edit, and leave these values as the default values. Don't change here anything, because we are using or simulating the air. And click on cell zone boundary conditions and click on edit here, and the CFD sphere body is going to be assigned with air. Here you can select the material name, it is air. So click on OK, and then go to the boundary conditions. This is the most important part. So at inlet, click on edit. At the inlet boundary condition, we are going to specify the velocity of 10 meters per second, and leave the turbulence values as default, and click on OK. And then click on outlet, click on edit, and outlet leave the gauge pressure as 0 pascals. So that is the standard method. We will give 0 at the outlet, so that the fluid flow is going to start from the inlet and flow towards the outlet. And the sphere is going to be wall. Edit and ensure it is specified with wall, stationary wall with no slip condition. Click on OK. You can also specify the surface roughness here. And interior has to be air as the fluid domain. we specified the inlet, we specified the outlet, we specified the wall condition to the sphere, and now we will select the symmetric boundary condition here. So automatically while you are naming the walls, if you give that symmetry, it is going to be automatically created as symmetry. And inlet is selected as velocity inlet, you can see here, and outlet is specified as pressure outlet, you can see it here. So we will specify the velocity inlet at the inlet and pressure outlet at the outlet. And finally walls. Walls are going to be a stationary wall, and I am going to give symmetry at the walls also symmetry condition, so that we will not be able to see any boundary layer on those walls, and all the boundary conditions are set up perfectly. Now we will go to the solution methods. So we will leave this as scheme as coupled, gradient as least square cell based, pressure as second order, momentum as second order upwind, turbulent kinetic energy first order upwind, dissipation rate first order upwind, and we will keep this as defaults. And controls also you will leave it as default values. And now we are going to specify the monitors. Residual plots. Here you are going to give 0.0001, that is 10 power minus 5, 0. After that 5 zeros and 1. Sorry, it is not 000, it is 10 power minus 5, so you will have 4 zeros. And you are going to go to the report files, click on new, or let me cancel this. There has to be a lift force and a drag force. Let me check where it is. Yeah, so it is here. Under the reports menu, go to the definitions, go to new, and then go to force report and go to lift. So we are going to identify the lift force. So here the force vector is directed towards the y direction. It has to be in the y direction actually, that is the lift force should be in z direction, sorry, lift force will be in the z direction. So in the z you will give 1, and at y you will give 0. Report plot, report file, print to console, and then you will click on OK. Okay, I didn't select the walls, so I will go and do it once again. I will select the sphere as my wall, and I will select the lift force, z direction 1, y direction 0. So this is the unit vector which is pointing towards the lift direction of the cylinder. So if you open up the Fusion 360, the lift force is directed along the z direction. So I will call it as lift force, and I will click on OK, and then I will go to definitions again, and then force report. This time it is drag force. I will write the name as drag force and select the drag force, and this time again select which direction it is drag force acting. So that is along y direction. So specify 1 along the y and 0 along the x. Select the wall, that is the sphere. So we are measuring the lift force and drag force acting on the sphere geometry. Click on OK and go to calculation activities. But before that we need to initialize. So click on hybrid initialization and click on initialize. So it is going to initialize the values for the first 10 iterations. So initialization is complete. Now we will go to the calculation activities. Auto save every iteration, that is 1. So let's say I will want to save it after every 10 iterations. And now click on the run calculation button, and you can see the number of iterations. Here I will give number of iterations as 1000, or let's say I will give 400 iterations, let's say, and reporting interval is after every iteration. So after I click on the run calculate button, it is running the simulation. So I have given 400 iterations. So currently we are at 4th iteration. So the problem earlier which we faced was due to the incorrect setting in the report definitions. So I deleted the incorrect ones and resolved only whatever is correct for us. So this simulation is going to take some time. So I will stop the recording and I will again show you the results file. So in this video we will see how you can convert the ANSYS Fluent mesh file into Simscale readable file or the OpenFOAM readable file. So we have exported the file previously. This is the mesh file .msh file. So I will just show you once again. So here you need to set the export type into ASCII instead of binary. I am opening the file and double click on the mesh. It is going to start the meshing interface for us. So this is your mesh inside of Workbench, that is Fluent. So you will first go to options and click on export options and set this format of input file as ASCII instead of binary. By default it will be binary. You need to set this to ASCII, otherwise the export will not work properly. And after you have done this step, again go to file and this time go to export and click on mesh and Fluent input file and then click on export and browse your folder and give the file name and click on save. And then the next step is to open command prompt. So here now I am going to enter into the WSL interface. So this is going to run Linux instead of Windows. So inside the Linux terminal, now I have to redirect to the D drive folder where I have saved the mesh file. So I created a separate OpenFOAM directory called OpenFOAM main, and in this I have created run, and inside elbow I have pasted the mesh sphere new mesh file. So we need to redirect to this particular folder in the command prompt. For that I will do cd space /mnt/d/ OpenFOAM main and inside OpenFOAM main I need to go to run. So cd space run and inside run again I need to go to elbow, and now the command to convert the .msh file into the OpenFOAM readable file is this. Fluent mesh to foam mesh peer new .msh, whatever the file name you want to convert, and hit enter. And it is going to take some time to run this command. Please wait for it. And now our mesh file is converted into OpenFOAM readable file. And now what you can do is you can create and open this para file. If you don't have this para file, you can simply go to the command prompt and say touch space para.foam. Already that file was created previously. You can see it here, para.foam. If you double click on that, it is going to open the para view for us. Click on apply. And now you can see the mesh being imported into the OpenFOAM para view. You can see the mesh which we generated in ANSYS Fluent being imported. We can see it in para view. Now close this, and now what you need to do is all the mesh files will be saved in this constant folder. So what you have to do is you have to convert this and compress it to zip file. And now you will import the zip file into the Simscale. So this is my file being saved in zip file. So this is what you will be importing. And now I will open the Simscale and I will upload the mesh here. I'll click on the plus button and click on import from computer. And this is our mesh file which is zipped. Click on open, and here it will ask you to choose the file format. Here you have to choose the file format as OpenFOAM and click on import. This is going to import us the mesh file directly into Simscale, and from here you can continue the tutorial of setting up your problem statement in Simscale and seeing the results. So hello everyone. So in continuation of the previous step where we see in the meshing part in ANSYS Fluent, so I converted that mesh into Simscale readable file using OpenFOAM, and now we are going to solve the same mesh problem using Simscale. So I will make a separate video on how you can convert the Fluent mesh into Simscale readable mesh using OpenFOAM, because that is another tedious task to do. And now we are selecting the incompressible fluid flow simulation using Simscale, and turbulence model is k omega SST, and time dependency is steady state. And I will select the material as air, and I will click on apply. And this is the region. Automatically the system is going to give us the default density and kinematic viscosity of air. We will use the default values, and now we will apply the boundary conditions. That is the velocity inlet at this particular phase, that is in the direction of y direction. So in the y direction I am going to enter 10 meters per second. Then I am going to apply pressure outlet at the outlet, and I am going to give a gauge pressure of 0, and then I am going to apply the symmetry condition at this particular phase. And again I am going to select symmetry and apply the remaining 3 walls. And I am going to apply simple no slip wall at the surface of the sphere, and I am going to go and create the plots for the forces and moments. So this is the sphere face. And I am going to also create the forces and moment coefficients. So this is not required as of now, so I will close it and delete it. And now I am going to select the simulation run. And as this Simscale is a cloud-based platform, once you start the simulation, you can log out of the system, and once the simulation is complete, you can again log in after some time, and then you can post process the results. So this is the basic tutorial. If you have any questions, reach out to me in the comment section. And so after the simulation is completed, it shows like this, finished. So you can click on the post process results in Simscale. And you can rotate the plane. Let me reduce it. And you can see how the flow is developing surrounding the sphere like this. and you can also plot the pressure. You can see the pressure plot, and our point of interest is the force plot. And click on forces and moments. And if we cut down the force in x direction and force in y direction, so this is the force in the z direction. I will open the same project in a different window to show you what are the directions of the fluid domain. So the drag plot is the force in the y direction. So you can see that a total force of 0.1 newtons is being applied. And the lift force is in the z direction. So the lift force is fluctuating because the geometry is unsteady in nature. Flow around a cylinder is an unsteady problem, so it keeps fluctuating about the mean position of x, the value of 0. And this is how you can post process the results using Simscale.